Hi, welcome back to McClatchy Maths. My name is Natalie McClatchy and today we are covering our second video in our series on Pythagoras' theorem and trigonometry by looking at Pythagoras in 3 dimensions. And this video is aimed at students from grade 9 up to grade 12. Grade 9 and 10, it's part of the extension part of your Australian curriculum, and grade 11 and 12 across Australia in a variety of different maths strands. In this particular video, we'll start off with some worked examples applying what we learned in the previous video. Then I'll have a quick talk about some of the types of problems you can encounter with these kinds of questions and tips to solve them. And then we'll have a look at what's coming up next in the series. So let's start with our first example. We have a store who sold a cylindrical drink bottle and wanted to place a straw inside so that its length was maximised and did not extend from the bottle. The diameter of the bottle is 4.4 centimetres and its height is 6.2 centimetres. How long should the straw be? So we've got some information in here about a drink bottle and we've been given its dimensions. We're not asked to find the area, we're not asked to find the volume, we're just asked to find out how long the straw would be, what's the longest straw we could put in the bottle so that when we put it in the bottle, it's not going to hang out at the top of the bottle. So I always think the best place to start is to draw a picture. So let's start and have a look at what a cylinder looks like for starters and put our dimensions that we're given in the question onto the actual picture. Now you can see that in this particular situation that with a cylindrical shape, that the longest part of the cylindrical shape is actually this diagonal that runs from the bottom left hand corner to the top right hand corner of the cylinder. I'm going to show you that now with an actual drink bottle. Here I have a jug that's going to represent my drink bottle and a straw. Now if I put my straw alongside the edge of the drink bottle, you can see that it's actually going to stick out the top. So I just need you to imagine that we want one that's not going to stick out of the top. So if I put this inside the jug like this, it's got an overhang right here. So what I want you to do is, if you've got one of these at home, I want you to put the straw at one end of the jug, and then I want you to tilt it across to the other side and put your fingers across the top like I've just done here. And that sort of measures how long the straw is sitting inside the jug. Now, if I straighten up my hand and make it parallel with the edge of the jug, you can see I've actually got about 1 centimetre or 2 centimetres overhang now on the jug. So you can really see here by doing this particular activity that when I run across the void space inside my jug, I'm actually going to get the longest straw running from the top corner of the jug to the bottom corner of the jug. Okay, something to note about the drink bottle is that the straw will be at its longest, as we previously mentioned, when it extends from the corner of one base to the opposite corner of the top of the drink bottle. And this is because our hypotenuse is always longer than the other two sides. We can see that that straw makes a shape of a triangle with the height of the cylinder and also the diameter of the cylinder. So our second step is to write the formula. C squared equals A squared plus B squared. And then we are going to substitute the information we've been given into the formula. Remember, our hypotenuse from our previous video is always C. We're trying to actually find C. That's quite nice for us. It's the subject of our equation. So we've substituted the base of 4.4 and the height of 6.2 into our formula, and now we need to evaluate that, showing all of our steps of working. So 4.4 squared is 19.36 and 6.2 squared is 38.44. Why don't you pause here and see if you can work out the actual length of the straw all by yourself, and then check in with me and see if you got all the steps of working written down properly and if you got your answer correct. So let's continue. C squared is equal to 57.8, and we can take the square root of that now and find that the length of the straw is 7.6 centimetres. Now, if you'll notice in the question for worked example 1, it didn't actually ask you to find C. It asked you how long should the straw be. So to answer that question, it's not enough just to write C equals 7.6 centimetres. We actually have to give a statement that answers the question that's been asked. So I'm going to start by writing a statement. I've already got C equals 7.6, and I'm going to now interpret that in a sentence. Hence, the longest the straw can be is 7.6 centimetres. Let's move on now to our second worked example. We're going to calculate the maximum length of an umbrella that could fit into a suitcase with dimensions of 1 metre by 1.5 metres by 0.5 metres. Now, a suitcase is typically a rectangle shape, and we're given 3 dimensions. We're not told it's a rectangular prism, but those 3 dimensions do lend itself to a rectangular prism. So it's always good, once again, to start with a picture. Before we actually draw that picture, I'm actually going to show you in a box what the diagonal would look like, and then we'll be able to mentally process what's happening. If you've got a box in your house and a ruler or a straight object, you could also follow along with this demonstration in your home too. I have here with me a cardboard box. This is going to represent my suitcase. As you can see, it's a rectangular prism. Now, I also have a ruler, and the ruler is going to represent my umbrella. And this umbrella happens to fit really snugly along the inside wall of my box. In fact, it's the same length as the box is. However, I could actually get a longer umbrella in here if I was to go across my diagonal there. As you can see, there's a bit of space left over. So I could actually fit an even longer umbrella across the base. Now you might conclude that that is the longest space within the box, but in fact it is not. If I look at my box from this angle here, from my top corner over here to my bottom corner over here, there is a diagonal that runs invisibly through the box. I'll show you now with this little prism here. Top corner up here to the base of the box. And this diagonal that runs across the top is actually the longest part of my box. I could fit an even bigger umbrella if I was to put it in the top part of my box here and run it along to the bottom part there. So that invisible hypotenuse that runs across that void inside the box is going to be my longest umbrella space. Okay, now that we've looked at our demonstration, let's draw the picture. We've got a box. Now, we've drawn our dimensions on, so we've got, it doesn't really matter where we put the 1 meter and the 1.5 and the 0.5 meters. It's going to work out the same regardless of which side we allocate to which. However, typically, our longest side will be that base there, the 1.5 meters along the bottom, and typically, the depth of the box would be shown as 1 meter and then the height as 0.5 meters. But as I said, it doesn't matter where you put your numbers. Now, as you can see, and as we showed before in the demonstration with the cardboard box, there is a triangle that sits inside the box. Its height goes against that back two corners. You can see that back there with the dotted line. Its base is Y, shown in green, and it runs as the diagonal along the base of the box. And then you've got this hypotenuse that sits inside the box, shown in pink, and that's X. It runs from the one corner of the top of the box to the opposite corner at the bottom of the box. So that's going to be the longest part of our box. You can try that yourself with the box. We already showed that in the demonstration, that that's the longest part of the box from one top corner to the other opposite bottom corner. So now that we've got our picture, it's actually a good idea to break this picture up into two separate triangles. And our first triangle is going to be 1 meter as its height, and then 1.5 meters, and you can see that's actually the base of the box. We've got that green side there with the Y, the unknown, and that's the hypotenuse of the triangle that sits in the base of the box. So that's our first triangle. Then we're going to have a second triangle. We've split that out now. That's that one that sits invisibly inside the box with its hypotenuse extending from one top corner to the other bottom corner, and that's shown in pink. So now that we've got two separate triangles, we can see that the Y from the first triangle is also an unknown in the second triangle. We've actually got to work out that first Y first. That will then come over to the second triangle, and then we can actually solve for X. So this is one of the typical things you see with these kinds of problems, is that you have one triangle, and then the information that you gather from that triangle will then move itself on to the second triangle, and then you can find your final answer by applying Pythagoras' theorem twice. So let's do that first with our first triangle. We're going to use the same variables that were on our original diagram. This is important. A lot of people often will then change it when they use their formula to A, B, and C, but if you've not got those variables on your original picture, it makes it very hard to solve properly. So we're going to start with the actual formula, c squared equals a squared plus b squared, but now I'm going to change all of the variables, not just the a and the b, which I have in my picture. I'm going to change c into y, so it's very clear to whoever's marking my work that I'm actually using that triangle. And then I'm going to solve in the way that we've always been solving Pythagoras' theorem. I'll work out y squared is 3.25 and take the square root. Y is going to be 1.8. Now I'm not finished. What I've found is the diagonal at the base of the box, on the inside of the box. So what I now need to use is that diagonal to find the hypotenuse of the diagonal that runs invisibly from the top end, which is actually the length of our umbrella. And that's going to be for x. So now I've got my original triangle that I had y on it. I'm going to change the y now to a 1.8 meters because that's what we've just found. And now it's a fairly straightforward solution to find x, the length of the umbrella. So once again, we write our formula, substitute into our formula. Notice here that c has been transformed into x because that's the variable that we have in our diagram. And we're going to process that a little bit further. X squared equals 3.49, take the square root, and we'll find x equals 1.87 meters. Now, once again, you've noticed that the question didn't ask you to find an x. It asked you to find the length of an umbrella. So we need to now write a statement. So we know x is 1.87, that's that invisible diagonal shown in pink. And we're going to write that therefore the longest umbrella that could fit into the suitcase is 1.87 meters. Let's have a very quick chat about the kinds of problems that you'll experience in these kinds of topics with 3 dimensions. So typically, the use of Pythagoras' theorem, as we've just seen in the last question with 3D, often involves using it to find the value of one missing side and then using that missing side on another triangle. So we're basically repeating the use of the formula over and over again, or in this case twice, to find a final solution. So as long as you're aware of that when there's 3 dimensions, that you could be looking for multiple triangles inside your rectangle and then taking what you know and then moving that on to what you don't know, then you'll be almost all the way there. So for example, you can also see lots of these kinds of problems with rectangular base pyramids. And in this particular diagram, there's loads of right-angled triangles. Pause here and see how many right-angled triangles you can spot inside this particular pyramid. Well, there are 4 in the base, as you can see. We've got 4 there. There are 2 on every outside face. I'm just showing you 1, but on every outside face there's 2. So if we've got 4 in the base, and then we've got 4 faces on the front, so that's 8 more there, so that's 12 right-angled triangles. And then there are 4 inside the void in that 3-dimensional shape that are not as obvious because they are made up of the height of the pyramid from the inside and that corner coming to the outside. So we've actually got 16 3-dimensional right-angled triangles inside our 3D shape. So that's a lot of triangles to work with, and these kind of problems can be a little bit overwhelming. So what you need to do is consider how finding the hypotenuse of one triangle, or finding a side using the hypotenuse of one triangle, can help you to find sides in another triangle. So we've just shown you there, if we just flick backwards and forwards there, if we knew the green information, the 146.71, we could actually work out the length of that diagonal on the base, and then we can flick that over and we can actually work out the value of S by translating that information across to the next triangle. There's also other ways to do that as well. So a strong grasp of this particular concept is going to lead you to greater success as we move on to trigonometry and bearings, because obviously we're only at the very beginning of our journey on trigonometry and Pythagoras' theorem, and these are the basic ones. So if we can work with 3 dimensions and start to draw diagrams or work with diagrams that really help us, then we are 90% of the way there. So some tips I have for problem solving. One of them is to use Polly's C-Plan Do Check model. You may actually have this model at your school that you've been practicing since junior school. Let me just give you a very quick overview in case you've never heard of this before. So C just means looking at the worded problem and identifying all of the key information. It could involve underlining, it could involve highlighting. Planning is where you think about maybe drawing a picture, and we did that in those particular questions. Part of our planning process was also looking for those 3-dimensional shapes in our home so that we could get a good mental grasp of what was happening. Planning also involves thinking about what kind of formulas that you can use and how you would use those to solve the problem. Do is actually doing it. That's where you're substituting into formulas, you're evaluating answers. And the very last step is very important, check. Check involves writing a statement, making sure that you have written your units of measurement at the end of every question, and also involves just checking some of those basic calculations, making sure your answer makes sense in the context of the problem. If you had to find a hypotenuse, a good question to ask, is the hypotenuse longer than the other two sides? Because if it's not, there's a problem. Okay. Some problems that we do come across with 3 dimensions, I acknowledge, they can be hard to visualize and draw, particularly if you're not a great artist. Imagine having to draw a square-based pyramid all by yourself. It can be kind of hard to do. If you're at home, it's a good idea, like I did, to go and find an object in that shape to help you visualize your problem. So go and grab a cardboard box, go and grab a drink bottle and play with that with a ruler or a straight object to see if you can work out how to find the side that you're looking for. Other times you're going to be provided with a diagram, and sometimes those diagrams are really helpful. But sometimes I've found, because my mind may work differently to the person who's created the problem, sometimes when I look at their 3-dimensional diagram, it's very difficult for me to understand. So that's why it's always important not to rely solely on the diagram that you're given, but to also read that extra information really carefully and see and make sure that that diagram is fully annotated, that you fully understand how it's all put together. Another good thing to do too is, if you've got 3-dimensional problems, is to break those out like we did in that last question into individual flat 2-dimensional triangles so that you can see how the problem is going to be solved. So we just talked about that there. And always annotate your drawings fully. When you're in an exam situation, it's really important that you make sure that all the information you're given is placed onto the triangles. If you then go and use variables in your working later on, like A, B, C, or X or Y, make sure those variables are actually on the diagrams, because those diagrams are often worth a mark or half a mark in an exam, and you won't get the mark if they're not annotated fully. And always write your statement at the very end. We've talked about that twice during the video. I don't need to harp about it for too long, but it's often worth a mark or half a mark, so it's really important that you take the time to write that statement. Okay, let's have a quick look at what's coming up in this series. We're going to kick straight into trigonometry, which is for our Year 9 and above students. We'll look at angles of elevation and depression, and then go into some bearings and problem solving. We're also going to cover off ways that we can use trigonometry to find area, ways that we can use trigonometry in the unit circle. So there's some later videos even further on in this series, so do stay tuned for all of that. And I'd like to say a huge welcome to anybody who's watching us for the first time. Welcome. And if you found this helpful, why not tell your teacher that you found this video on the internet and it really, really helped you process your work. Share it with a friend. You could also follow on Facebook and Instagram. We have some fun stuff there from time to time. Hopefully some more competitions coming in the future. And you could like the video, subscribe, and hit that bell so that you always know when I have a new video ready for you to watch. And I'd like to also let you know that you can contact us via our email address, mcclutchymass@yahoo.com, and you can also contact us via Messenger and Facebook and Instagram using the direct message function. That's probably the best place to ask involved questions or to ask for further assistance. If you pop it in the comment, I do read all the comments and I often comment back on those, but it's not a great space for giving a great deal of detail. Well, once again, thank you so much for joining me. You've been watching McClutchy Maths. I'm Natalie McClutchy. Have a wonderful day.